Today we're going to talk about double Holliday junctions and crossing over. Now, during crossing over in meiosis, essentially what happens is this form of DNA repair. Specifically, let's suppose we draw the two duplexes of DNA that engage in crossing over. 5 prime, 3 prime, 3 prime, 5 prime. And just to make things easy, we do a little trick and we put 3 prime on this side here, and 5 prime there, and 5 prime here, and 3 prime here. Now we need to keep track of the genetic information that gets exchanged during crossing over. And so we're going to basically distinguish this duplex from this duplex by putting big A, big B, big C, big D, likewise. And then little a, little b, little c, little d, likewise. So the first thing that happens during crossing over is a double-stranded break occurs. Right there. Bingo. Okay? It actually is induced by an enzyme called SPO11. And the next step, making sure that we keep our 3 prime and 5 prime ends indicated, is that it's the 5 prime ends then that get eaten away. So the 5 prime end gets eaten away around this double-stranded break like this, and the 5 prime again of the double-stranded break gets eaten away like this. Now notice something. 5 prime end, 5 prime end. Because the 5 prime ends of DNA cannot grow, this end is not going to be able to be templated off of this big B here. Likewise, this end here cannot retemplate off of this big C. So in some form, this big B information is at some level lost here and lost here. How is that repair, how is that crossing over then established with this structure? Well, the first thing that happens, we can visualize, is there's something called single end invasion. So this end here, this 3 prime end, is going to invade this duplex, and it's going to pop out a structure called a D loop. And basically, you need to imagine it kind of coming in like this, and then sitting here at that locus through the C pairing, okay? And then popping little b and little c up like this. And what's important when you do this is to maintain the 3 prime, 5 prime polarity when drawing these types of structures. So the 3 prime end is going to invade from here. This structure is going to pop out and form the D loop. So we have like this. Little b, little c, and then the end that invades. Okay, big C here. Now notice something. This big C is now in complex with this little c. This is what we call a heteroduplex. And this will result in gene conversion at some point. Now, what's important now to notice is that now what we have is we have an ability to read in this direction this 3 prime end, because it's a 3 prime end that grows, and now this will template DNA polymerization in this fashion, little b of course being put there, and likewise templated in this direction, little c right there. And there's a ligation event that occurs like that, and there's a ligation event that occurs like that. Now what we can see is now this hole that was left with big B and this hole that was left as big C right here has actually been converted into little b and little c. Now how do we resolve this structure? The way it gets resolved is a bunch of different possibilities. One possibility is we simply cut and ligate these ends together here, and cut and ligate these ends together here, cut and ligate these ends together here, and cut and ligate these ends together here. And you can basically conceptualize this as a cut and ligation like this, and a cut and ligation like this. When that happens, basically big A and big A here, and big B here, don't exchange with one another. They stay on the same duplex. And that leads to non-crossing over, but importantly, we still have these events of gene conversion here and gene conversion here. And if the heteroduplex gets resolved, where this, say, for example, big B gets turned into a little b, or this big C gets converted into a little c, that would be another example of gene conversion. Now, we can also have resolution happen in a different way, where we don't basically cut and resect these ends, cut and religate those ends. We actually would have a cut here, cut here, cut here, cut here. And then ligation would be forming in this fashion. Now if it both happens on this way and on this way, what this then does is essentially it switches big A over here and flips it and exchanges it with little a. But likewise, big D's are being switched with little d's. So again, that doesn't result in a crossing over because big A is staying with big D. How do we get a crossing over? We get a crossing over when the resolution is different between the two sides of the double Holliday junction there. So specifically, what we would do is we might, for example, resolve right here in this fashion, but maintain resolution like there in that fashion. What that means is that the big D's are going to switch over like that, but the big A's are going to stay on the same side. And so, for example, then big A would actually be recombined into the little d's, and we would have crossing over. But the important thing to remember is that during crossing over and in non-crossing over, there are still these patches of gene conversion that happen at the site of the double-stranded break.